Mm. All right. So we're trying to sync together this information. So let's say I had a phase portrait, not a phase portrait, but I had this like direction field, and let's call that 3 right there. And then let's say there's actually, well, that's pretty shitty. So these dash lines, these are going to be equilibrium solutions. Wherever I put a dashed line, and then I'll put one at -1 as well. -1, and then that's 0. And let's say I've got, now I got to be really careful here. So I got to think in my head how this is going to work. So let's see. So this one's going to be sloping up down here. Then as we approach that equilibrium, things will chill out. And then this one's going to be like this inside here. And the trajectories inside here, let me do them in red. So down here, the trajectories are going to look like this. And here, they're going to be like doubly asymptotic. So they're going to be asymptotic to the equilibria at 0 and then the equilibrium at -1. And then in here, let's say we've got this deal like this. And so the equilibrium solutions will look like that. And then last one, I've got these up here, and I'm going to have an unstable equilibrium up here. And so whoop, things like that up there. So I want to work this backwards. I'm trying to engineer this backwards to the autonomous DE for which this could be the D field for. So that means, so the first thing I would do, Kayla, is I would come down and I would kind of work backwards to first the flow on the line. So let's say here's X, and I've got these 1, 2, 3 different equilibria. So I've got one at 0, I've got one at 3, and Sydney, you are also concerned about this one too. So we got that. And then this one at -1 is stable. I've got a half stable at 0. And so it's stable on the right, unstable on the left. And then the one at 3, is this right? Yeah, the one at 3 is completely unstable. So far, so good. Is that making sense? Like moving? Yeah. Okay. Cool. So that means this flow here is like this. Whoop. Nope, not at all like that. Actually, like that. Okay. So that's like first step. Step 2 is. Well, thought I heard something weird. I am hearing something weird. Like feedback or something. Every time I talk, you're like, yep, little bit. So I've got to come up with this portrait, and this is really what it's all about. This phase portrait, the relationship between X dot and X. And so these zeros, going to have a 0 here, 1, 2, 3 here, and then 1 here. So I've actually just got to create, basically I would come up with like a polynomial curve that when I employed it here, it would give me that flow. So notice that to the right of 3, we have a positive flow. So that means down here, the graph has to be above 0 to the right of 3. And then that flow is negative between 0 and 3. So that means this graph would have to come under like that. Okay, are you following? Yeah, cool.
Yeah. In the textbook, our equilibrium solutions are a solid line.
Oh, yeah, I'm just doing them like that to make them
Okay.
a little more yes.
Okay.
So
catch on.
sorry.
No, I'm saying when I read the textbook, I didn't understand that that's what that meant.
Oh, got you.
So
Got
I
you.
thought that they just put a nice happy horizontal line in there, and I was like, that's awesome. I'm so glad. Okay, cool.
Yes, that is
This
a little
makes-
confusing. So seeing, look, and I'm such a like people pleaser, I instantly just did it to make you happy. I was like, okay, well, if that's what she wants, we'll do that too. No,
Thank you.
I've got to say no sometimes, Kate.
To me, or just in general?
Okay, just in general.
Okay.
Okay, no, I'll put them back. See, I can't even freaking do it. Just kidding. Okay, so, and then I'm positive here. So up, now here's the tricky part, and here's like a little bit of, I don't think you're going to actually have this in the one that I'm seeing there, but we'll know how to do it. Notice that, oh,
Doesn't it bounce at 0?
this is actually incorrect. Yes, this should be below 0, shouldn't it? Because this is negative here. So that should be like that. And then it comes up and it's positive. So to come up with a polynomial like that, I'm just going to use the fundamental theorem of algebra with also the knowledge that when I bounce off, and I think I'd mentioned this, when you bounce off the x-axis, you have a even power. So that's the trick here. So this one, let's see here. We need 0 at -1. We need a 0 at 0. So let's put that like that. And then we need a 0 at 3. And the 0 at 0, we have to bounce off of. So I'm going to make that x squared. And then I just have to make sure that I would plot this out on like Desmos and make sure that I get the right looking polynomial. In other words, that it's not this dude here like that. But it's not, and I can tell it's not. Can you see why it's not? Can anybody tell me why I know that I'm okay? Why I know that's cool without graphing it?
Well, the x to the 4 power is positive, so then it should be up like a cup.
Beautiful. Yeah, so when you go to plus or minus infinity, you go upwards when the x goes. Yeah, perfect. So that's how I do this one. But probably those horizontal lines were the thing maybe throwing you off the most. Yeah. Sydney, feeling cool about that? And Trinity, you're good on this one? Outstanding. Cool. What else would you like to talk about? Anything? Did the chemical one work out okay?
Can I ask a clarifying question about that one?
You can ask it. You could probably answer chemistry questions better than me.
So for A,
Yes, I'm sorry. This was 232. Is that correct?
yes.
Okay, got it. Yes, ma'am.
So I pulled an x out, so I factored an x out of f of x,
Good.
just so that you have an easy fixed point.
Mhm.
So then your other x star should be k1a over k minus 1.
That sounds right. Let's check that out together. But your approach sounds right on. So yeah, pull out that x and then so yeah, a 0 at x equals 0 and then a 0 when this equals 0. So yeah, that would be k1a over k minus 1. I think that's exactly what you said.
Okay, cool. So we know that both rate constants are positive parameters, so we really only have one case. When we're doing our like line, okay, the little line thing that we just did, how would we think about that on the left hand side and the right hand side of that fixed point?
Okay. So I think let me get there and then maybe we can talk more about what it is you're asking. So we've got a fixed point here. I'm not going to color them in yet. And then we have a fixed point here. And then, like you said, everything's positive. So this would be K1A for K minus 1 here. And when you plot that out, you're going to get an upside down parabola. Yeah, does that make sense? Because this is a negative x squared, a negative something x squared, so it'll open down. So can you, so like from here, could you maybe clarify a little about what you mean?
I think I was trying to approach this in the wrong way. This makes more sense.
Oh, cool.
Because I could just use, got it, cool, great.
You're probably trying to get too fancy with it, is what I'm thinking.
I don't know about that.
Just roll with it. Yeah, you were trying to be too
That's
sophisticated.
exactly what I was doing.
Yeah. Cool. Let's see. So that's part A of that, and then part. And the interpretation. Do you have to interpret this stuff? No.
We just need to sketch x of t values. Whoa, for various values.
Got it. So that's going to be, this is going to be the x versus t down here, and you're going to have your equilibrium at K1A over K minus 1, and then just figure out the right flow in there.
Okay.
With the little arrows, and then, whatever trajectories. This isn't right, what I'm doing here, deliberately so, but something like that.
Okay. So then when it says various values of x naught, we're actually saying the equilibrium solutions.
So no, so what we're saying is we want to consider these trajectories that I just sketched for various. So there's like, let's see, let me back up. So there's really 3 regions of interest here. And so if you started up here, what would the solution do? If you started, well, if you start on an equilibrium, you know what it's going to do. It's going to stay there. If you started in here somewhere, and if you started down here somewhere. So denoting what those qualities of those regions produce.
Okay.
Yeah.
Cool.
Anything else? We good? Okay. Cool. So I think those are due on Friday. Is that correct? Yes. Outstanding. And I'm just going to hold off. I've got some new problems that'll be based on the stuff we're going to talk about today a little bit, but I'll just hold off on those. So you got time to finish this up. And I kind of want to create some ones on my own anyway. So like homemade problems. Groovy. All right. Let's talk about bifurcations. Keep talking. We're going to be talking about this for a while. And I don't know if you had a chance to start reading that chapter. Anybody get a chance to start on that? Yeah, Trinity, you're kind of like, yeah. And we can, and we will start like reading that. So Trinity, you might, I don't know how far you got, but some of this stuff gets really heavy. Like, and we're not gonna go into every depth of it. So like in the beginning of this book, he talks about what kind of courses you could make from this book. And there's the one kind of course where it's basically graduate level, and we really get into all those examples, and we try to understand every single little detail of like the physics applications and all that kind of stuff. And that's not the kind of course this is going to be. this is going to be just a course where we come out of here stronger and hopefully for Trinity covering some stuff that you've never seen before. It's kind of hard when your high school basically was like a aerospace academy or whatever, but you know, I want you challenged. I want you challenged at some point. And don't think that I'm making this course easy by any stretch. But there's certain like math skills that I want you to come out with that I kind of don't think you probably have ways of looking at problems. And we're going to start doing that today. So I promise you will be powerful when you leave here. So let's talk some more about bifurcations. And these are just bifurcations in the flow line or on the flow line. We will start talking about bifurcations in the plane eventually, but we got to get this kind of figured out first. So let me just ask you before we go on, just like in your head, what is the definition of bifurcation? What is a bifurcation? Like in your head, just like like you're explaining it to yourself, you're tutoring yourself. Yourself says, what is, you ask yourself, what is a bifurcation? And then you answer, what is the answer? So cool, karma-free quiz. Anybody care to regale us with their definition?
It's a split.
What is a bifurcation?
It's a split.
Yes, absolutely. Yeah, absolutely. Right. Like, and that word is used in the law and things like that too. You know, do you split some case into two different parts? What does it mean in terms of a dynamical system? So that I agree, Kayla. Yeah, like that is definitely part of it. Can we like elaborate? What else is it? How does the word quality, how could we incorporate the word quality into our definition? Or qualitative? Okay, and I'll tell you. so we don't have to hang here too long. So a bifurcation is a qualitative change in the nature of the equilibria of a dynamical system. So it's a big change in the long-term behavior of our solutions. And if we think about it in terms of the flow in the plane, it's the flow in the plane looks and acts completely different after a bifurcation. And sometimes, and there's like some really bad jokes in all math books. And in this one, he talks about the pitchfork bifurcation being maybe it's even a trifurcation, which is pretty goofy. But so this is all. So just because it says bifurcation does not necessarily mean there's only a splitting, but there is a splitting. Generally, in equilibria moves from a single to multiple. So you were right on, Kayla. I wasn't saying you were wrong at all. So the first job that we have is to understand the three basic types of bifurcations we can encounter and how to analyze them mathematically. And it's in the mathematical analysis that I think the fun and the learning is going to really come. So let's just kind of go through them. So we have three major types. And the first one is what's called a saddle node bifurcation. Now, when you think saddle, you might be thinking, like especially in math, thinking of like a hyperbolic paraboloid, or maybe you're not thinking of that at all, but like a saddle shape, literally like the shape of a horse saddle is, it's curved. It looks like a parabola in one direction that's facing down, and in the other direction it looks like a parabola that's facing up. So generally, a saddle node is this thing that is the max of one of those parabolas and the min of another. What we're going to do now does not look at all like that, but a parabola is involved. We won't really see the saddle nodiness of this until later. That will reveal itself later, but it's going to take more dimensions of study than we have right now. So this is like a saddle point right here that I've drawn. But for us, so there's a couple other names for this. It's also can be called a blue sky bifurcation, which is really a pretty name for things. And that's kind of a flavor of saddle node bifurcation. And then I think there's one other name, and I can't remember what it is, but if you read the book, he mentions it. It doesn't matter. We're going to call them saddle node bifurcations. So the basic form, so there's kind of these canonical forms. And they take the form of algebraic equations, just simple polynomials. But in real life and in practice, which we'll see in our homework and the problems we do together, that it doesn't always look like this. And you have to really dig deep to see the parabola hidden in the structure. And we're going to use Taylor series to see those in some ways, right? The Taylor series are our microscopes, our mathematical microscopes. So canonical form. So first off, we've just got x dot equals r plus x squared. This is one kind. R can be positive or negative, but we could also have this x dot equals r minus x squared. And those will give us the different flavors of saddle point. In the end, it's all the same action. But let's start with this one here first. So he doesn't start off like this in explaining what this might be, but I'm going to, because I think that to work with these, there's a trick. And we're going to start with the trick right off the bat. So first off, let's think about the equilibria. So the equilibrium solutions. And here again, so R is our parameter. That's our control knob, right? So you've got this R knob, and it's got different values from 0 on up to plus infinity, and then the other way down to minus infinity. And there might be restrictions on that, but for now, we got this little control knob. So our equilibrium solutions are going to be when the flow stops. And that's going to be when x, the state of the system, satisfies this equation. I'm going to rewrite this. So instead of just going in here and solving, like doing algebra, taking the square root, all that stuff, I want to think about this geometrically. That's a huge part of this class, just learning how to analyze equations in a geometric way. And you're going to be able to take this stuff and use it other places besides studying bifurcations. But let's take a look at this again. So I'm just copying it up here. What we have here is really the intersection. So we can think of this. So can think of as the intersection of two curves. The first one is y equals negative r, just a horizontal line, because r is a constant, and y equals x squared. And this is the trick in understanding how to decide what is happening as the parameter r changes. So then you sketch these out. And we're going to come over here, and we've got y equals negative r. So now I've got like different cases. Let's take a look here. Let's say that r is positive. So that y equals negative r looks like this. And this is negative r right here. And so the way I've drawn that picture, r must be positive, because if r is 3, then that's y equals negative 3, for example. And then the other one, and I'm going to say this and then I'm going to stop. And then the other one is just yield parabola. Like this. So this is y equals x squared. And then this one is y equals negative r. Let me stop and make sure that this is all making sense. Is there anything that I need to clarify or could clarify? Or does sound
What are
okay?
these?
Yeah.
Are these still x and x dot?
Not for this analysis right here, Kayla. We're kind of like keeping it in the back of our mind. But what we're going to actually do is think of just the algebraic solutions to this thing, keeping in mind that they will be the equilibrium solutions of that x dot equation. Does that make sense? Yeah. Okay. Awesome. Awesome. Beautiful. All righty. Cool. So the R knob controls that line. So I've got this horizontal line and it moves up and down. And right now, when R is greater than 0, what are the places where it touches? Well, nowhere, right? So here there's no intersections here. So no intersections. And what that means is that there's no solutions to that equation, so no equilibria. But imagine what happens as I start to turn R to 0. So as R goes to 0, this line moves up. And at R equals 0, and this is where you do this in your head. You make this on paper, and then you play the game in your head. So we're going to turn R down. We're coming back, right? Because the larger R gets, the further that line gets away from the parabola, and things just get worse. But as that line moves toward the parabola, so let's make the next picture here. So when R equals 0, that's the first moment that they touch. And this is a bifurcation because the state of this system has changed. There was no equilibria, and then suddenly something appears. So let's put the parabola back. There's y equals x squared. And now my line is right here, literally on the x-axis. And I have one intersection point. So at this moment, as soon as R hits 0, boom, the steady state appears. And so we have one equilibrium at x equals 0. Is this making sense? Yeah, cool. And then, so then I'm going to keep turning R down. So the R becomes negative, which means negative R. So negative R becomes positive when R is a negative number. So the minute I've got R is negative, we have this. We have our line has moved up. So there's y equals negative R. And we've got yield parabola. like so. And now we've got two equilibriums. So this is what Kayla was talking about earlier. That one equilibrium has split into two. And you can literally see this. We're going to look at a little movie thing here in a minute. I found an amazing app page that we can do this on, so that it's not just all in our heads, but I think understanding on paper is essential as a first step. So what we've seen is that as I move R, so here's R, and here are my fixed points, X stars. So this is fixed points, i.e. equilibrium. So now I'm going to look at a plot. When R is a positive number, there's no equilibrium. So over here, there's no equilibrium. The minute R hits 0, 1 appears. And as R becomes more negative, those two green points on the parabola move further and further apart. And so what we see here is that as we move from left to right, we had two equilibrium. Now we haven't analyzed their stability, but we will in just a second. We have two equilibrium. As we move to the right, as R increases, those get closer together, they merge and then disappear. So this is the classic saddle node bifurcation right here. Two equilibria meet, annihilate each other, and there are no more equilibria. So right here, this is the bifurcation diagram, but we have to fix it a little bit because I don't have stability indicated for a saddle node bifurcation. So we can do all the analysis right here on this page. We just have to remember from whence we came. So I'm going to put in yellow up here the original equation. So remember the original equation was this: x dot equals r plus x squared. And we don't have to do any stability analysis when there are no equilibria. So that's totally cool. So when R equals 0, now let's actually look at the phase portraits for this. So for this one, sorry, over here. So phase portraits for equilibrium states. So the first one was R equals 0, and here's what the equation looks like. X dot equals x squared. And so come down, I plot that. Here's now x dot versus x. And now we're back there, Kayla, and we're definitely going to do that. So there's my phase portrait, relating the change in x to the state of x. And here I can make the flow line now. Positive, positive. So I've got a half stable equilibrium at 0. When R was negative, we had x dot equals x squared plus r. So think about that. That's just the parabola. I don't want that black line. That's just the parabola shifted down. And its vertex is literally at negative r. Where are the equilibrium solutions now? So what are those 2 points and what are their stability? So I ask you, just take a moment, if you could, and answer that question. So each of those has a formula. What is the formula for them? And what is their stability? And let me get my little app up here. Boy, that's loud. You hear all that popping? Can you hear that popping out there? Oh, geez, that's weird. I'm sorry. Little popcorn. I don't know how to stop that. Maybe it's this page here. Yep, cool. Cool. Very groovy. Okay, cool. All righty, so that was a little, again, karma-free quiz. R is a negative number. So when I solve this thing for the equilibria, so to find x star, I'm going to set x dot equal to 0. So we get 0 equals x squared plus r. And we subtract that r off. And we're cool because r is negative. So that left side is a positive number. And I'm not going to get an imaginary solution. So x is plus or minus square root of negative r. So this is positive square root of negative r, and this is negative square root of negative r. And those are our equilibria. And then we go to do stability, and you can see the parabola is below here. So we flow to the left. We have a negative flow. Here we have positive flow, and here we have a positive flow. So I've got a stable and an unstable. So notice how the half stable was stable on the left, unstable on the right, and that split into a stable moving out to the left and an unstable moving out to the right. So when we do our official bifurcation diagram, it's going to look like this. Notice that the stable one is on the negative x-axis. So if I'm doing r and then x, and we can call this x star, I guess, that the stable one is on the bottom. And the unstable one we mark with dotted lines. So there's our official diagram. Any questions at all on getting that done? No? Cool. Cool. So here it is in like a much more glorious form, actually, here. Let's see, can I do this? Can I do what I want to do here? Yeah, cool. So this app, I actually put a link for this app in the content area. But this is so cool. I think I need to learn how to make these because I'm jealous of the person who has this knowledge. But here we can see that parabola, and you could, what's nice is you can see the flow on the left. So watch, so there, the minute I hit 0, that equilibria appears in the slope field. And so you see the stability from the left side and the instability on the right side. And then as we become a little more negative and just a hair's breadth, instantly that thing splits. And then you've got 2 equilibria. Let's get them a little further apart. Again, the bottom one stable, top one unstable. So I just think that's fun. I think that's just quite beautiful. So this is in there for you to play with all you want. Let's see, what's this one here? Oh, and then here's the way we thought about it, right? That line moving toward the parabola and then creating those two. So that's a saddle node. Let's come back to here. This is the classic saddle node. The blue sky bifurcation looks like this. So for a blue sky, it's just really a reversed saddle node bifurcation where here's our equilibria, here's our parameter, and nothing happens on the left side. And then as r becomes positive, we see, as soon as R becomes 0, we see a half stable point emerge, a stable branch, and an unstable branch are created as we move to the right. So blue skies, same thing, just in reverse. Probably something like this. Just put a negative in front of the R so that the behavior is reversed on, as R becomes positive, then you can actually get real solutions to this thing. Sound okay? Because I want to do something more interesting, and we're definitely going to take a while on this material, because I want to do a real analysis, not that class, but an actual analysis of one of these. So let me grab a problem out of here, and let's see if we can do this. So 311 is kind of fun. I really like 311. I like all these problems. So in 311, we've got this system. And they tell us, show that a saddle node bifurcation occurs at some R value. So I guess I'd like to actually kind of set you loose with this with just the tiniest bit of guidance while we're all here together, and then we'll come back together. So let's think, what has to happen to understand this? So we're searching for equilibriums. So x dot is going to equal 0 when negative x squared is equal to 1 plus rx. And that's going to happen. I'll get you rolling. So negative x squared is this. What's the other side? So this is y equals negative x squared. What's the other side look like geometrically? Got to get my volume up. I can't hear you. Let's see. Let me turn the volume. So can anyone just in words tell me what this looks like?
A line.
Yes.
Slope. Or well, if it doesn't have to be positive, it will go like this, but it intersects the axis at 1.
Beautiful. So a line of slope R, y-intercept 1. Perfect. So this guy is going to be right here. And then if R is negative, the slope could look like this. If R was positive, it would be on the other side. Yeah. What R value? So this is 1 plus Rx. I want you to take a minute. At what R value do those first touch? There's two of them. So we could think of this is R's negative here. Here's R positive. Oh boy, that's pretty bad. So here's my first question. At what R value is because once we find that, we've actually found a place where the state changes. We find where an equilibrium point either emerges or is destroyed, depending on what direction we're thinking about this flowing. But it's those tangents that give us the moment of bifurcation. This is fun. Like this is like, this whole class is freaking math club, basically a little private math club that we have every Oh yeah, Ms. Trinity. I did go through your paper. I don't know if you saw, I left some comments in there, and we should like talk, like just like, I would love to talk about it. Just so much easier than writing shit out. So maybe tomorrow or Friday we could figure out something.
Yeah, we can figure out a time to talk about it. I was also trying to plan a meeting with all of us.
Oh, okay.
I'll just be on the same page.
Okay. Cool.
So,
That sounds
but
good.
we can meet just one-on-one too, though, because that'll be helpful.
Okay, cool.
Okay.
But good work. Very
Thank
good
you.
work. Yes. But I feel like I have actually helpful things to say, which is, it feels good. Yeah. If you're not quite sure where to start, first semester calculus with derivatives and the derivative being the slope is a real good place to start. You think you got something, Kayla?
I'm using Desmos because I want to.
No, it's okay.
I will stop using Desmos.
No. I love that you're using Desmos. Desmos, it's hard not to want to use Desmos.
I want to watch the little slider. Does that make sense?
Oh, that's cool. So you like set up a parameterized thing. Oh,
Is that
how
okay?
could I not want you to do that?
Okay.
I mean,
I can take the derivative of a second degree polynomial, I promise.
I know you can.
Okay.
That's good. I totally know you can. I like that. Desmos is good shit. So I'm gonna start doing it. Sans Desmos here. But yeah, I love doing those parameterized curves on Desmos. So much fun. And I totally did that while thinking about today. So we're each in good company here. Tangent slope. So like when I was trying to answer this question, and there's probably there's many other ways to do this. It's just like this is how my mind rolled on it. Is that when you have this parabola like this negative x squared parabola, the tangent slope at any, oh my God, that is sad. That's just so fucking sad. Hold on. Better, less sad. The tangent slope at any point x, and I'm totally cheesing that as well. So m is equal to -2 times the x coordinate, right? It took first derivative. The slope of that line is r. So at what point on this parabola do I have a slope of r? And the answer is at -r/2. And so r can be positive and r can be negative. This is when r is less than 0, and this is when r is greater than 0 over here. But that's the moment of bifurcation. So I have I actually have two different bifurcations that'll occur in this system. One is at a positive value of r, and one is at a negative value of r. What happens after r moves past those points? So like there's this whole range. Oh yeah, let's see here. So here's r positive, here's r negative, here's r 0 right here, right? So here's r equals 0. So what happens as r becomes more negative than that? And what I see is this happening. So here's my parabola. Sorry for the red. Come back to this. We had this line through 1. And at this moment right here, we've got, and we still haven't found that exact x coordinate yet, but we will in just a second. So that's the moment of bifurcation when that happens. But then as r becomes more negative, this happens. And what we see are two intersection points forming. So you get that one moment of when the bifurcation occurs, and then you see it splitting into two as that line becomes more and more negative. I'm going to do what Kayla did so we can see that actually. So I'm going to get me some Desmos out here. I might even, I have the Desmos app. Yes. So yes, beautiful. So I'm going to do two different equations here. So first one I'm going to do is -x squared. And then the other one I'm going to do is 1 plus rx. And you can just enter a number. If you haven't ever done this, you can just enter any other letter besides x or y. For you kind of find it. It helps to not be blind. And then you click add a slider because it knows that's not one of the standard variables, x, and we got that. Is this how you did it, Kayla? Like with two different curves? Cool. So then you can move your little slider. I like to set the step to be something a little bit more precise. So like 0.1. And then here, probably 5 and -5 would work for that. Oh, it doesn't like that. It wants 0.1. Okay, no problem. We'll fix that. So now I can move this. So here's R becoming more negative. There's the moment of bifurcation and then the splitting. Yeah. And so we see that occurring. And then we've got to figure out where are these points at. So that's when we need to come back to the algebra. So let's see, what was the actual, what does Desmos estimate that to be? -2 on one side and then +2. So this gives us a sense of like, you know, are we doing this right or not? +2 on the other side. How would I actually end up getting those? So let's talk about how I could actually get that moment for those new equilibria. So coming back to here, cleaning it up, coming back, put my picture back. God dang. And then line going like this. This point here. So I know that at that moment, the slope, the tangent slope is -r. So m equals our r here. And I also remember my original equations that this has to also satisfy x squared plus 1 plus rx has to equal 0. And we decided that this also had to happen when the tangent slope on the parabola, -2x, equaled the slope of the line. So x has to equal -r/2. So I'm going to take that. I'm going to take that, and I'm going to get an equation in r. Or I can get an equation in x. Either way, I could solve this bottom one here for x. So in other words, r equals -2x. I could plug that into the top equation. And in fact, let's just do that. So we're going to combine these. And so I'm going to get x squared plus 1 plus -2x times x equals 0. And all I'm doing is replacing this r value with this thing here. And then I come down and simplify. So I got x squared plus 1 minus 2x squared equals 0. So okay, everything's cool. I got scared for a second. So 1 minus x squared equals 0. So x equals plus or minus 1. What scared me was that I had said something about r being 2 and -2. But that's okay, because it is. That's the bifurcation parameter, because I still have that. So the moment at tangency here occurs when x equals 1, and over here when x is -1. So if I was looking at my bifurcation diagram, so let's put a couple other things here. When x equals 1, the bifurcation parameter is -2. And I'm getting that from this relationship right here. And then over here, when x equals -1, the bifurcation parameter is +2. So that means down here in the bifurcation diagram, I've got a bifurcation that occurs at 2 and at -2. And at that point, check it out. So when I'm at -2, x is equal to 1. And when I'm at +2, x is equal to -1. And then after as x increases past +2, decreases past +2, whoa, wait, let's see here. It's the slope. Yeah, so as x gets steeper, or the slope gets steeper, then this guy is going to split into two different things. And then as x becomes more negative, then we also see the splitting into two different things. Last thing to do is to adjust the stability. So put dotted lines or solid lines. And to do that, then I have to actually go in here and decide in this thing here, x dot equals x squared plus 1 plus rx. I got to get in here and figure out, is x dot positive or negative in each of these regions? And that'll require a little bit more work that I think I'm going to ask you to do. So what I would like you to do as a problem for, I don't know, let's talk about it on Monday. That would be really cool if we could talk about it on Monday. So like your only task for Monday would be to fix this bifurcation diagram to add the stability. Make one of the branches will be dotted on each of those curves and one will be solid. Which is which? Does that sound okay? Yeah. And then maybe we could just, like, you could write that up and turn it in at the beginning of class on Wednesday. That would be super lovely. Yeah, write this all up, make it look really pretty. And I think hopefully in doing so that like it'll kind of gel if it hasn't gelled already. And then I might give you another one, but I won't make it due on Wednesday. That's okay.
Monday or Wednesday?
I would like to be able to talk. I don't know. Do you think do you think you'd be able to get this done by Monday's class? Would you prefer it be start of Wednesday's class? You all tell me, like, we're in this together. Start of Wednesday's class sound better? Somebody give me guidance here, ladies. Give me some guidance.
I think Monday would be okay.
Okay, let's shoot for Monday. And you know that, like, if we need to talk about it, that'll be fine. How about we try to have this done for Monday and then we'll just talk about it. That would just be great. Yay. Okay, cool. Decisions are so challenging sometimes. Yeah, and then I'll give you like a full-fledged one to do after this, but this is like a nice warm up. So actually, and I would add to this as well, so here's what I'd like. Complete the bifurcation diagram. And with all details. Yeah, that's all I want. I don't know. For some reason, I thought I was going to get more excited about that, but that's just it. That'll be plenty. That'll be hunky-dory. And how about we call it a day, since some people aren't even meeting today and you've already done more than many of your peers. And then I think Miss Kayla and I need to talk about some advising stuff or something.
Yes, please.
And Trinity, well, let's figure out something. I can meet by Zoom tomorrow at almost any. I have this like interview with the Department of Corrections in the afternoon. Not because I'm going to prison, but because like I'm going to be teaching a class for inmates next fall, and they're doing like this background check on me. So they want to see if I have integrity, and somehow they'll discern that from this phone conversation. So I have that in the afternoon, but we could do anything, and I'll be on campus on Friday, so we could meet in person maybe too. Or next week, whenever, we'll get it figured out. But I'm available, or this weekend, if you even want to like just do a Zoom conference this coming weekend. I'm all for that.
Okay, I'll email you what works best.
Okay.
Okay.
Sounds good. We'll make it happen. Awesome. All right. Well, otherwise, Sydney, have a lovely weekend.
Thank you.
Have
Thank you,
some
Dr.
snow
T.
fun. Thank you. I'll see you on Monday. And Trinity will talk before then. And Kayla will talk now. I will stop recording.
Oh, cool.